That's not what I want. Okay. I'm not sharing the screen yet, am I?
No, but you should be able to.
Yeah. All right, do we see it now?
Yeah.
Yeah. All right, so the last time we talked about the basic simulation types, you know, the .op simulation, .dc, .ac, .transient, and .noise, okay? And the intent of that was just to talk about the different simulation types and to walk us through how to perform them. And this time I want to talk more at a little bit of a higher level about why. Why do we simulate circuits? Why do we use this tool that we call a simulator? What's it good for in the general, in the grander scheme of things? Okay, so we're going to talk about the role of simulation in our lives as engineers. So let's see. All right, so what is simulation good for? Simulators, I want you to think of a simulator as a power tool. Sort of like if you were to think of some of the fundamental tools if you wanted to build something like a screwdriver or pliers. Hold on, guys, sorry. If you were to think of some of the fundamental tools that you would use if you wanted to build stuff, something like a screwdriver or pliers or things like that, that would be somewhat analogous to your analytical skills, your ability to do math, to perform nodal analysis and solve matrix equations and things like that. And certainly they're powerful and useful and fundamental, but you can do them faster if you have, say, a power screwdriver, like a power drill. You can get through jobs much faster. And at the end of the day, an engineer, the intent of an engineer is to get a job done, not necessarily to sit down and show how good you are at doing math. You need to be good at doing math. You need to know how to analyze circuits. You need to do that because then you can gain a truly deep understanding of what you're doing. But at the end of the day, you want to get a job done. And when you want to get a job done, you want your power tools. Okay, so in the name of getting jobs done, you want to have power tools and you want to have them in your toolkit, because if you don't and somebody else does, they're going to get the job done first, and they're going to get paid and you're not. Okay, so you want to have simulators in your toolkit. Steve Jobs had a wonderful quote: "A computer is the equivalent of a bicycle for our minds. A simulator is the same thing for analyzing circuits." So simulators can analyze and verify circuits very rapidly. But again, you know, you want to be able to do analysis on paper to develop your analytical skills and intuition, but that raw analysis is frequently very cumbersome and time consuming. Things like transcendental equations that you encountered in your microelectronics class, calculating pole and zero frequencies that you might have encountered in your control systems class. Figuring out the corner cases for all of the components, if all of the components in your circuit shifted by a certain percentage, right? Figuring all of those things out is just very time consuming and not very practical to do by hand all the time. Simulating a circuit is much faster than building it and testing it. And not only is it's faster than analyzing, which is great, but it's also faster than building it and testing it. And the reason why you would want to build and test a circuit, of course, is to figure out if it's actually going to work. So before you get to the stage of building and testing your circuit, it's good to simulate it just to verify that at the very least that the idea is sound. Okay, because you can miss stuff when you analyze circuits. You know, you think you know what's going on, but very frequently you forget something or you miss something. It's great to be able to do analysis having made some assumptions, but at the end of the day, you know, it's not your analysis that matters. It's whether the circuit in real life works that matters. And simulation is kind of this intermediate step between analysis and building the circuit. Furthermore, simulation also helps your intuition. Why? Because your intuition is developed. Your intuition is basically your ability to look at a circuit and very rapidly be able um, to to visualize waveforms, visualize voltages and currents as a function of time or as a function of frequency. Um, and it's hard to develop intuition without exposure. And simulation gives you the ability to get a lot of exposure to a lot of different circuits. And it can give you that exposure because it's relatively cheap to try ideas. Right. If you come up with some novel circuit idea, you can actually try it instead of having to build it every time. Because, if buying the components and building a circuit, getting a PCB designed, that entire process can take weeks. And all of that just to try an idea. Well, what if the idea didn't work? What if it was a bad idea? Right? Like you would have a very long turnaround time to figure out that your ideas are flawed. So, or to find out that your idea is a good idea. So a simulator works as this great little rapid loop to be able to develop circuits, develop ideas, try them out, and see if they're sound or not before you invest in actually building the circuit. And also simulation can help your intuition beyond that, because simulation allows you to use truly ideal components that don't exist in real life. Ideal components such as voltage sources and current sources and transconductors. And you can, if you want, you can add or remove these ideal components. And that enables really quick hypothesis testing. So say, for example, if you were to build a circuit and it wasn't working, it might be because of some parasitic behavior. It may be because of some parasitic inductance or parasitic capacitance or something like that. And it's really difficult to tell what exactly is wrong with the circuit unless you can add or subtract those parasitic components, which is really difficult to do in real life. But in a simulator, it's really easy to do. Right. And so in that way, simulation allows you to build intuition by the ability to add and remove ideal components. Okay. What is simulation bad for? Right. It's really tempting. A lot of people are really tempted to use simulators at every opportunity that they have, and with good reason, because simulators are it's very rapid and quick to test ideas in simulation, but they do have their drawbacks. Simulators can only simulate what you have modeled. Okay, anything that you have drawn in the simulator, voltage sources, current sources, resistors, transconductors, inductors, those are the exact components that are going to be simulated when you run your simulation. However, your real circuit is going to be something different than what you put in your simulator. Generally speaking, that is always the truth. Just how different is it? That sort of depends on your skill at modeling the simulated circuit to be representative of the real life circuit. And in any way that your model is not representative of the physical reality, things like component variation, parasitic capacitance and inductance, interference, your simulation is never perfectly accurate. And this is also true of hand calculations, right? Analysis on paper. Nothing is ever truly accurate because what you build is never perfectly the same as what you have done math on. You've always made some certain assumptions. For example, you've made an assumption that a 100 kilo ohm resistor is exactly 100 kilo ohms, but in real life, it might be 101.2 or something like that. Right. If you didn't model that, if you didn't put that into your simulation or into your hand analysis, then it would not be reflected in your simulation. So in generally speaking, a physical circuit will never be exactly what you simulated for exactly those reasons. So really, like, simulation is good for building a basic model of your circuit to confirm basic function. And you can progressively make the model more complex to make it more accurately representative of what the real circuit would be like. But ultimately, your simulation will never be perfectly accurate. And so recognizing that what really matters is how the real circuit performs in real life, right? That's what really matters. The simulation really just is kind of an intermediate tool in between the idea that you got in your head and what you will build in real life. It's this intermediate stage where you get to try out your idea and play with it a little bit and see if the idea itself is sound and if there are any glaring mistakes in your idea. And if you have reasonable confidence in your idea and you feel like there's not a whole lot more that you can get out of simulation, that's probably a good point to actually build the circuit. Furthermore, if you've already built a circuit, sometimes running the simulation can be slower than testing the actual circuit in real life, right? I mean, if the circuit hasn't been built yet, this isn't true. But if you've already built the circuit, then testing the circuit in real life can often be faster. This is especially true for circuits that have a periodically oscillating nonlinear circuit, like a power electronics circuit, like say measuring the loop gain of a switching power converter, or measuring the phase noise of a PLL or something like that. These simulations can run really, really slowly. So sometimes it's just more practical just to test the circuit in real life. If you already got the thing built, just test it in real life. All that said, though, you know, simulation is really, it's just a really, really useful tool. And it's great to have in your toolkit. All right, so let's work through an example. This is an op-amp circuit, a gain of -10 op-amp circuit with a load capacitance of 200 nanofarads. And let's see if we can simulate the behavior of this circuit. Okay, so here we would be working with a provided model. Let me just go ahead and show you how I might go through this. Okay, so let's start a new schematic. And what I'll do is I'll use the add component dialog, and I will type in LT1006. Okay, and I will click on the schematic. Okay, right click to escape that. I'll add a couple of voltage sources to power it. So I'll add dialog, voltage source. Here's one, here's a second one. I'll add a ground between them. And I'll call the voltage source, well, let's give it a value of 15 volts. So I'm going to power this op-amp from plus and minus 15 volts. And I'll give the power supply node some names. So use the hotkey. For you, it's probably F4. And I'll call this VCC. And I'll call this one VEE. Right click to escape. Okay. Oh, I want to copy that over to the power supply terminals for the op-amp. So let me just copy. I'll just copy the name, the node name. Copy VEE. Boom. Okay. So now we've got our op-amp and it's powered. Let's configure it so that it has the inverting amplifier configuration. So I'll ground its non-inverting input, and I'll take its inverting input and attach it to a couple of resistors. I'll have an input resistor and a feedback resistor. Let me just drag this. And we'll just go ahead and draw a wire to close the feedback loop. I'll make this a 1K resistor. Right click this, make it a 10K resistor. And we'll add a load capacitor. 200 nano. Okay. I'll give this a name. I'll call this out. I can make this an output node by right-clicking it and saying port type output. Let me just take this wire and move it over. Okay. I'll give this one, I'll call this one input, port type input. Okay. It just makes it look nice. Okay. Okay, so I've got the thing, I've got the op-amp on the page, on the schematic. I've got it configured as an inverting amplifier. I have its load, I have its power supply. Now I need a signal source. So let me just hook up, I'll just copy one of these power supplies. I'll copy this over and I'll add a ground. Okay, so this is my input and I'll right click it and I'll hit advanced. So instead of having a DC value, I'm going to set it to a piecewise linear. And its start value is 0 at 0 time. And at 1 nanosecond, it is -1 volt. Okay. All right, and I need to do a transient analysis. So s.tran 500 microseconds. I'll place that on the schematic. Okay, so we should be all set. We've got the op amp, we've got it powered, we've got it configured as an inverting amplifier. It has a load, and we have a signal source, and we're running a transient simulation. This should go. The running man. And let me just tile like so. Okay. Let's go ahead and plot the output there. Okay, there we go. All right, so we have an input voltage that is stepping from 0 to -1 volt. And if we plot the output voltage goes to plus 10 volts. It eventually settles out to 10 volts. It does have this strange behavior initially, though. It seems to be going in a straight line rather than your standard linear circuit behavior, rather than a standard second order system. So it has these weird shapes, and then it also seems to be ringing a little bit and so forth. But it does eventually settle down at 10 volts, just like you would expect for an inverting amplifier with a gain of -10. Okay, cool. So there you go. We've simulated a circuit. By the way, if I want to try a different op amp, I can always just go to the add dialog and double click on op amps and scroll through the many op amps. Which one did I pick? LT1006. So this is the one that I picked, but I could try perhaps an LT1007 and place that on the schematic, cut this one out and place the LT1007 and then give that a try and see what happens. Ooh, it behaves differently. It seems to be faster or something, but it's ringing a lot more. Okay, let me just undo that. Undo, undo, undo. Okay. Hit the running man and run it again. All right, cool. So that's how it goes with a provided model. Now, there are some pros and cons to simply running a simulation using the provided model. Namely, on the pro side, running a simulation using a provided model, like I just showed you, a provided model for an op amp, is that on the pro side, it's really quick to start, right? You know that you have to put an op amp on the page and power it, and then configure it in whatever amplifier configuration that you want, and it'll run, right? So it's pretty quick to start. It pretty accurately models the behavior of that op amp, or at the very least, it models the behavior that the manufacturer of that component that provided the model, that manufacturer thought was relevant, which often is a sufficient model to get you in the ballpark at least. And if one op amp doesn't work for your circuit, then you can often just pick a different op amp and see if that op amp works. And well, sometimes it'll work and sometimes it won't. On the downside, you don't know what is and what is not modeled by the manufacturer in that model. And furthermore, if your circuit isn't working right, you don't know why. For example, you might see that your circuit's not working right, and then you say, oh, well, let me just pick a different op amp. And then you drop a different op amp in, and then that one's not working. And then you pick a different op amp, and that one's not working, right? So you don't necessarily know why your circuit isn't working if all that you're doing is just trying randomly different op amps, right? So that's kind of the downside of using the provided model. It doesn't give you any transparency into what parameters of the op amp are relevant to making your circuit work. Is it the gain bandwidth product? Is it the output impedance? Is it the slew rate that is insufficient? If your circuit is not working, right, you don't know why unless you have some acute insight into knowing how op amps work. If you've taken a 442 class, perhaps, then you might have some better insight. But even then, you know, it takes some time and experience to figure out how to get stuff to work. So if your circuit isn't working right, you just don't know why unless you have lots of experience. Is there a problem with your circuit topology or with the op amp that you chose? Maybe you're violating the power supply or common mode input voltage requirements, right? It's kind of hard to debug. So I'll show you another way of going about things. So this is using an ideal op amp, or at least almost ideal. Let me show you how to set up a simulation where you have a pretty much ideal op amp. So let me just create a new schematic, and I'll just go ahead and copy. I enter the copy mode and just drag a box around everything. And I'll copy this schematic into this schematic, okay? Escape. And I'll minimize that. So instead of having an op amp model, I'll just have an ideal op amp, or almost ideal. So as you know from your introductory electronics course, an ideal op amp is an amplifier that has infinite gain, infinite differential gain. Being a numerical solver, LT-Spice does not permit actual infinity, but we can get close enough. I'll add a component, and I will add an E component, which is a voltage-dependent voltage source. And I'll just go ahead and drop that on the schematic. Okay, so its output is going to be ground referred, and its input is going to be a differential input measuring the difference between this node and ground. Okay, and as long as I make the gain of this, the voltage conversion gain of this component very large, close to infinity, then it should work. So let me right click on it, and where it says E, the value, I'm going to set that to something really big. I'll set it to 1 giga, meaning 1 gigavolt per volt. Okay, so what is that, 10 to the power of 12? So that's a pretty large gain, close enough to infinity, that this should do the trick. So let's just go ahead and hit the Running Man. And there we go. So let me go ahead and, okay. So now we have an input step that goes from 0 to -1 volt, and the output voltage steps from 0 to 10 at essentially the same speed within a nanosecond, which is how fast the input step was as defined by that piecewise linear voltage step. Okay, so so according to if we could somehow fashion an ideal op amp, then this circuit would work properly with no overshoot and no ringing, and it would simply have a gain of -10, as you would expect from your introductory op amps, or rather from your introductory circuits course. Okay, so let's make the model a little bit more sophisticated. Perhaps we can, find at what level of sophistication the circuit starts to see behavior that we are not as happy with. So we can model some more complex behavior. I'm going to model the behavior of an op amp that takes into account its limited gain bandwidth product. This is a topic that you'll get into in Engineering 442, which is your op amps class, if you haven't already. So instead of just an infinite gain voltage dependent voltage source, instead what we'll do is we'll model a voltage dependent voltage source that has a single pole associated with it. How are we going to do that? I'll show you. So I'm going to drag this voltage source over, and instead I'm going to right click on it, and I'm going to give it a value of just 1, okay? Bear with me. I'm going to cut this wire. Now, in order to have something that has a single pole, I need to add another node, a node that's going to have a pole associated with it. In order to do so, I'm going to add a component. This time I'm going to add a voltage-dependent current source, and I'm going to use this current source as the gain element. Okay, like so. And I'm just going to give it a value of, say, 1 milli, meaning 1 milliamp per volt. Okay. All right. Yep, let me just cut this. Okay. Now, to implement a pole, I'm going to add a capacitor. And to model the effects of limited gain, I'm going to add a resistor. Okay, let's add a couple grounds there. I'm going to make the value of this capacitor 159 picofarads. I'm going to make the value of this resistor 100 mega ohm. Okay. All right. Now, let's go ahead and add a ground there. Okay, what exactly happened? So I'm just going to draw a box around this. This stuff right here, this is modeling the op amp now. Now I'm creating a slightly more sophisticated model of the op amp. that still has very large gain, at least at DC, but at higher frequencies, its gain starts to drop because this current source, instead of just feeding a resistor, begins to feed this capacitor as well. Okay, so the gain of this op amp at DC is 1 milli times 100 meg, which is 100K, or 10 to the power of 5. Okay, that's its DC gain. But at high frequency, its gain reduces and becomes the gain of a 1 millisiemens current source feeding a 159 picofarad capacitor, which, if you do the math, gives you unity gain at 1 megahertz. Okay, and then we just take this voltage and recreate it here with basically a voltage buffer. Okay, so this models the behavior of a fairly typical op amp, at least the AC behavior of a fairly typical op amp. All right, let's go ahead and hit the running man and see what happens. Okay, not too much. I mean, we do notice if we zoom in on that initial step, we do now notice that instead of the step being instantaneous, occurring within 1 nanosecond, it behaves kind of like a single pole, sort of a low pass filter. If I look at the tau, I'm just going to kind of hand wavy. The tau of this appears to be about 2 microseconds, which is, well, we could do the math on that. Now I'll leave that as an exercise for you, what you expect the time constant associated with this to be. It would have to do with the gain bandwidth product of this op amp being 1 megahertz, as well as the loop gain being brought down by a factor of 11 due to this feedback divider. But anyway, okay, so, but it looks like it has a single pole response, but there's no ringing, there's nothing unexpected or anything like that. And by the way, if you want to see the AC response of this amplifier, I could do an AC simulation. Let's say .AC decade 100 points per decade from 10 hertz to 100 megahertz. I'll just drop that on the schematic. Control right click on the transient command. That brings up this edit text dialog, and I can convert it to a comment. And let me just right click on this voltage source and give it an AC amplitude of 1 so that it'll actually run in an AC simulation. Let's hit the running man. And here we go. If I look at the output voltage, I can see that indeed at low frequency is 20 decibels, or 19.999 decibels. And then it appears to have a pole. The pole frequency appears to be around 100 kilohertz. And well, actually about 90 something kilohertz. And then it starts to roll off at about 20 decibels per decade. Okay. So we can, it's nice that we get to see these simulations. We get to, see the AC response as well as the transient response. And all that it takes is just commenting and uncommenting, and we can swap back and forth between looking at AC response and transient response. Okay, but nothing too unexpected yet. Maybe we can see what happens if we model some of the slew rate limitations. So if I want to implement a model that shows the slew rate limitations, what I'll do is I'll take this current source, or I'll take this this transconductor G1, and I'll make it so that it's current limited, so that when the voltage difference between its inputs exceeds some value, that it will saturate at a particular current. It's basically mimicking the behavior of a differential pair at the input of an op amp. So let's just go ahead and right click it. And instead of its value just being a fixed value, I'll give it a value that is a table. Table, parentheses, from minus 0.1 volts. So when its input is minus 0.1 volts differential, its value will be minus 0.1 milliamp. And when its input value is 0.1 volts, its output value should be 0.1 milliamp. Okay. Let me just move that somewhere else out of the way. Okay, now let's hit the running man. Okay. So what do we observe now? What we observe is that after the initial step is applied, the output voltage rises. It doesn't appear to rise exponentially just yet. It rises in a straight line. And that's because, let me just go ahead and add a plot pane. If I were to plot the current coming out of this current source, it is a fixed value at first before it then, before it finally assumes a linear response. Let me just go ahead and undo that a couple times, and I'll show you the difference. Okay, so I just reran it after undoing that, and you can see that the peak value of that current is close to 1 milliamp, and it has this exponential response in both the current coming out of that current source as well as the output voltage. But if I redo and then rerun, now we have a constant current, and this is not called a linear response. This is actually a nonlinear response for the output voltage. The output voltage simply continues in a straight line, but it's not a linear response. And then eventually, both of them assume an exponential decay once the commanded current falls below some particular value as specified by the table. Okay. Do we have any questions so far on how that's working?
I had a question that was more going back to sort of like the beginning of the presentation and modeling circuits. Let's say you have a fairly complex board that you're working with. They don't create SPICE models for something like a microcontroller, correct?
Correct.
Okay, so this is more for like the, yeah, okay. Just wanted to ask that.
Yeah, so what you would do if you have a microcontroller in your circuit, and basically the SPICE simulator is really intending to model the analog behavior of your circuit. Whatever behavior is digital doesn't really need simulation. At least it doesn't need like this level of simulation, if that makes sense.
Yeah, I'm thinking about like if I'm looking at a motor and I'm trying to figure out sort of like the feedback and interplay that it has on a circuit, like maybe that's more made for like a Simulink model rather than.
There are ways to model motors, but I haven't planned any way to. I haven't planned covering it in this presentation.
That's fine.
Yeah, there are ways to model motors, and then there are ways to model logic, but I'm not covering it at the moment. It's a good topic. You can actually look it up. It's not easy, but it's not impossible either.
Cool.
You could do it with Simulink. I think the difficulty between doing it in Simulink and doing it in SPICE is going to be likely similar. The primary advantage of doing it in SPICE being that whatever skills that you develop will be transferable because LT SPICE is free, and you can bring that skill anywhere.
Good point. Good point.
But you would have to look it up. It doesn't come with like the SPICE tutorial. You'd have to find it on the user group. Okay, right. So let's go back, continuing the discussion on modeling this op-amp. Let's see if we can figure out what about the op-amp was making it do that weird stuff. So let's just model the output impedance. Here I'll go. I'm going to drag this over, and I'll add a resistor to model the op-amp's output resistance. This will be 100 ohms. So right now, let me just kind of back up a little bit and say this stuff right here inside the box is now my model of an op-amp. It's still not the most accurate model in the world, but it is a more sophisticated model than just your ideal op-amp model. All right, let's hit the running man and see what happens. There we go. Let me just cut this waveform of the current coming out of that current source. Okay, this actually looks kind of sort of similar to what you saw with the op-amp model for the LT1006. You saw a certain amount of overshoot and ringing until eventually it settled. There's some differences, but you know, without getting too sophisticated into a model, you know, this more or less shows what we were observing. So the lesson that you would take away from performing this train of thought would be that by developing uh, progressively more sophisticated models of the op amp, you could eventually find what parameter of the op amp was responsible for causing the undesired behavior. In this case, it was the output impedance, in combination with the bandwidth and so forth. We can go ahead and play around with the bandwidth as well. You know, let's suppose that we wanted an op amp that was 10 times faster. We could simply change that capacitance and see what happens. And you know, there you go. This is what would happen if you picked an op amp that was 10 times faster and had all the other, you know, all the output impedance and the DC gain and so forth, all the same. Okay, you get to play with that so that eventually, when it comes time to pick an op amp, you know better what to look for. Or if you have a good idea of what op amps are on the market, you know, you would have a better idea of for what reasons they may be inappropriate and for what reasons you may have to build an additional circuit or something to get your idea to work. Okay, so so some of the op amp parameters that could be modeled, we showed how to model the gain bandwidth product limit, the slew rate, and the output impedance. But there's a bunch of other things that you can model that we didn't show, like the output voltage range, common mode input voltage range, the ESD clamping diodes that protect the non-inverting and inverting inputs of the op amp, the power supply rejection ratio, common mode rejection ratio, offset, noise, input capacitance, input bias current, package parasitic inductance, and you could go on and on and on for days and days, making a progressively more accurate model. But typically, it suffices to just model perhaps the first three, and beyond that, just kind of go with whatever, you know, those are the ones that really help you understand which parameters of an op amp may make it appropriate or inappropriate for a particular circuit. And then beyond that, you could just, you know, pick an op amp and use its model, and, you know, see how it goes. So in summary, like, I just used an op amp as an illustrative model to show that process, but it could be any component, right? And what I was trying to demonstrate there, though, is that simulators are excellent power tools for quickly developing circuits, testing your ideas and intuitions. But then furthermore, being able to test where your ideas may break down when you try to use an actual component. And you have to be aware, though. You have to be aware when you're using simulators. People often like to say that simulators are shit in, shit out. Namely, if your model is too inaccurate, then the real circuit will behave very differently than what you have simulated. And so, you know, some people who are not very good circuit designers will just simulate something that's entirely bogus and then claim that they have created a circuit that does something amazing. But in reality, you know, it's an infeasible circuit because they've simulated a circuit using components that don't exist, right? Or that are impossible to obtain. Right, so there's no point really. You can hypothesize about the behavior of virtually any circuit that you want. If you could find an infinite bandwidth transistor or whatever, you could, you know, in theory, you can create a circuit that does anything. But that's not very useful, right? What you want to do, what's more interesting, is the ability to create circuits that do something useful using components that are actually available in the physical world. So it's the onus is on you as a user of a simulator to build or use models that are reasonably representative of what happens in the real world. And if you don't, then your simulation is completely useless. And at some point, the physical circuit has to be constructed anyway. So one might say, well, why perform a simulation? Well, because when you run a simulation, at the very least, your circuit, your design has received greater scrutiny than just a hand calculation. right? You could walk into, I mean, you know, it's tempting. It's very tempting as, you know, a fresh engineer to say, you know what, I know how this circuit should work. I'm just going to go ahead and build it because I know how it's going to work. But I would say probably about 95% of the time, even if you're an experienced circuit designer, there's going to be something that you didn't anticipate, that you just did not think through, especially for circuits that have lots of nonlinear behavior, things like switching circuits, say a motor driver or something like that, where, you know, some transistors turn on and the other transistors turn off, and you're trying to figure out the sequence of events. You know, there's just all sorts of behavior that is not very intuitive. And even if you have an intuition, it may not be perfect, right? So, you know, about 95% of the time, I would say that that you just don't get it right. And so it's it's very useful to run a simulation to, at the very least, prove out your idea or test your idea before you build the thing, and that can save you a lot of time and help you troubleshoot and figure out, you know, if your idea is problematic, how it's problematic, and how to fix it. So within the flow of circuit design, it's often best to implement a circuit using ideal components first, because that allows you to prove out that the basic idea is sound. Then bit by bit, you can replace those ideal components with more realistic components, like we did with that op amp, to verify the circuit behavior in the presence of these non-idealities, you know, non-infinite gain bandwidth product, or, you know, non-zero output impedance, or whatever. If the overall circuit stops functioning properly, at the very least, you know where to start looking. And in the process of troubleshooting, you can compare model variations to see what aspect of the component is preventing the circuit from functioning properly. You can change the output impedance, you can change the gain bandwidth product of your op amp, or whatever. You just play around with it to figure out what parameter is troublesome. Okay, so let's just walk through quickly how to perform simulations, to perform a couple more simulations that get a little bit more advanced. Simulations that allow you to really prove out circuit ideas. So previously we showed how to run DC, AC, transient simulations, and those show how, those prove that an idea is at least capable of functioning. Then at some point you want to make sure that your idea is a robust idea. How does that mean? Okay, so let's just go ahead and walk through an illustrative example. I'm going to create a circuit, and I'll drop in a component, NPN, and I will right click on it and pick a new transistor, make it a 2N3904. Okay, and then I'll add a current source. I'll rotate, Control R, and then I'll add a voltage source. Add a few grounds, draw some wires. Okay, I'll make this voltage source of 0 volts, and I'll make this current source. Instead of giving it a value, so I've right-clicked on the current source, right? Instead of just typing in a value, I'm going to add curly braces, curly left brace, and I'll call it IB, curly right brace. It's arbitrary what I typed in there. I'm just going to pick IB. So that's a variable name. I've picked a variable name called IB. So I'm going to say, let's add a spice command, S. I'm going to say dot param IB equals 1 milli. So IB is going to be a 1 milli quantity. And when I parameterize it into a current source, it's going to be 1 milliamp. All right, so let's do a DC sweep. Oops, sorry. S. I'm going to type .dc V1 for the voltage source connected to the collector. I'm going to sweep it from 0 volts to 10 volts. Place that on the schematic and hit the running man. Okay, let's tile that like so. So now I'm going to plot the current that flows into his collector. Now this should be a plot that's fairly familiar to you, that you've seen in your microelectronics classes. Okay, so when the voltage from collector to emitter is very small, then the transistor is in saturation, and then At some point, the transistor goes into active, and the current becomes approximately constant, with some slight variation due to the early effect, or otherwise known as base width modulation. Okay, now that's how we set a parameter. So what I've done is I've parameterized the current that feeds the base of this transistor, and then I've given that parameter a value. Where this becomes interesting, it's not too interesting yet, but where it becomes interesting is when I can step it. So I'm going to add another spice command, S, and I'm going to type dot step param IB, and it's going to be stepped from 1 milli to 10 milli in step sizes of 1 milli. Okay. Now let me just go ahead and right click that so you can kind of see. This is the dialog that appears for it. So the name of the parameter to sweep is IB. It's going to be a linear sweep. You can also pick a decade or an octave, like a logarithmic sweep, or you could do a list where you list out all of the values. I'm just going to do a linear sweep. That's going to sweep from 1 milliamp to 10 milliamps in increments of 1 milliamp. Okay, so let's hit the running man. Okay, there you go. So this should be yet another thing that you've seen in your microelectronics class. So again, on the x-axis, we are sweeping the voltage applied from collector to emitter. So that's VCE. And on the y-axis, we're plotting the collector current, the current that's flowing into the collector. And what we observe is that when the collector emitter voltage is small, is in saturation, the transistor is in saturation. And then when the collector emitter voltage is greater than approximately 0.2 volts, then the transistor enters active and the current becomes approximately constant with a slight upward slope. And the value of that current depends on the base current. How do I know which one is which? Well, if I click, just left click on the title, then I bring up a cursor. And the cursor is currently, the cursor is currently on the green waveform. It's kind of hard to see, but it's on the green waveform. And if I want to know which step that was, I can right click on the cursor. If I right click, then it shows me cursor 1, that's the name of the cursor, and it tells me which step it was on, or it's currently attached to. IB, that parameter, is equal to 1 milli. Okay, if I click the up and down arrow keys, then that allows me to bring the cursor from one waveform to another, from one step to another. So pressing up on the up arrow causes the cursor to move to a later step, and pressing down brings me to an earlier step. So let me just bring it to this red waveform. So now the cursor's on this red waveform. Let me right click, and it says the red waveform occurred when the base current is 2 milliamps. Press up all the way, and it should be 10 milliamps of base current. Yep. Okay. So that's how you step a parameter, and you can generate a whole sequence of plots based on the steps of that parameter, and you can compare the plots, and you can bring a cursor between those different plots to compare all of those different plots against each other. Let's do something a little bit more interesting. So let's suppose I wanted to measure the output impedance. We often call it RO, the RO of this transistor. Here's what I'll do. I'll add another spice command and say .mes dc RO find. Actually, you know what? Let me just type .mes and add it to the schematic. And I'm going to use the dialog. I'm going to right click it, and it brings up this fancy dialog for a .measure command. Applicable analysis, it's a DC sweep. Result name, I'm going to call it RO. The genre, that's a find. Measured quantity, 1 divided by the derivative of the collector current of Q1. The derivative of the collector current with respect to the collector emitter voltage tells you the conductance. And dividing, taking the inverse of that tells you the small signal resistance, RO. And I'm just going to say, I'm going to find that value at 5 volts. In other words, when VCE is equal to 5. Okay. Well, it's not going to do anything just yet. Let me hit the running man again. Okay, so nothing changed yet. In order to see the result of that measurement, you have to view the error log. View spice error log, or alternatively, Control L. So we bring up this error log, and here it shows all of the steps that the base current went through. And then we also see the results of these measurements. And we can see that on step 1, when the base current was 1 milliamp, the RO was 500 ohms. And on step 10, at 10 milliamps of base current, it's 109 ohms, or 110 ohms of output resistance. We can also do something cool. If I right-click on this dialog, I can plot the stepped measurement data. Let me just click that. And the only thing that we've measured is RO, so it automatically brought that up. So here we are plotting the RO of the transistor as a function of the base current, because this is the stepped parameter. Let's make this 1 milliamp so it looks nicer. Okay, so this is the stepped parameter that was stepped from 1 milliamp to 10 milliamp, and you can see that RO is essentially inversely proportional to the base current, which, if you remember anything about microelectronics, is to be expected. Okay. All right, any questions on that so far? Okay. So let's move right ahead. Let's talk about doing some corner simulations. I'm going to add, I'm just going to model a low pass filter here. So I'm going to stimulate this low pass filter with a voltage source. I'm going to add a resistor and add a capacitor. So nothing too special about this low pass filter just yet. It's just a first order low pass filter, like you would have learned from your introductory circuits course. And let's just give this a, let's just give this a name. I'm going to call this the output of our low pass filter. Now, I'm going to do something a little, well, let me just do this first. I'm going to give this advanced, give it an AC amplitude of 1 volt. And just to make sure it works first, let me just make this a 1K resistor, and I'll make this a 1 nanofarad capacitor. And I'll say dot AC decade 100, 159 to 159 megahertz. Okay, let's hit the running man. And we'll do that. Okay. All right, so it looks like a low pass filter, and its 3 dB frequency is at 159 kilohertz, which is what you would calculate from the 1K and the 1K ohm and 1 nanofarad. Okay, cool. Now, let's suppose that you were going to build this low pass filter in large quantities. And when you purchase this resistor, it is specified by the manufacturer as being a plus or minus 5% resistor. And when you purchase this capacitor, it's specified as a plus or minus 20% capacitor, which is very common. These are very common tolerances for these types of components. What would it do to your low pass filter? Well, one thing that you could do would be to do some hand math, to do some hand calculations. But for a sufficiently sophisticated circuit, it becomes pretty cumbersome to do that. Especially, I mean, for a single pole low pass filter, it's not too bad. But if you had, say, a 4-pole or a 6-pole filter, it can get pretty tedious. So we can kind of shortcut that a bit by just using the simulator. So here's what I'm going to do. I'm going to parameterize the resistance. I'm going to right-click on the resistor. I'm going to set its resistance to open curly brace 1K times, and then I'm going to put in parentheses 1 plus R corner. Okay. So what that means is I'm scaling 1K by a factor that's equal to 1 initially, but I'm going to add or subtract some amount based on a parameter that I'm going to call R corner. Same thing for the capacitor. I'm going to give it a value 1 nano times 1 plus C corner. Okay, So now I'm going to have to add these parameters. I could say dot param r corner to set its initial value, 0, and c corner equals 0, just to make sure that it still works and I didn't break anything. Okay, cool. And then I'm going to step param r corner list minus 0.05, 0.05. And we're going to hit Control Enter to add a new line. Step param c corner list minus 0.2 plus 0.2. Okay, so now we're going to step both of those parameters to cover plus or minus 5% and plus or minus 20%. Okay, hit the running man. And now we get to see all 4 corner cases. They're called corner cases because these are the corners of each component. Each component could be plus some tolerance or minus some tolerance. Generally speaking, when you purchase a component, it has very low probability of being actually at the corner. But at the very least, if you verify that your circuit is going to be functional when the component is at that corner case, then you can be pretty confident that when you build it, it will function properly, regardless of which component happened, where in the manufacturing batch that component happened to come out of. And I can use that dot measure statement again just to show it off. Dot mes. Let me place that, and I'll right click it. So I bring up the dialog. In this case, we're performing an AC analysis. So applicable analysis AC. Result name, I'm going to call it bandwidth. This will be the 3 dB bandwidth. And what we're going to do is we're going to, oops, not derivative. We're going to find the frequency when the absolute value of the voltage is equal to 1 divided by the square root of 2. Oh, let me just cut that out. I don't want it to be there. Okay. All right, so I'll just rerun it. And if we look at the error log, Control L for the error log, then we see that at one corner, its cutoff frequency was 209 kilohertz. At another corner, it was 189 kilohertz. At another corner, it was 139 kilohertz. And at the last corner, it was at 126 kilohertz. So that's a fairly large range of frequencies, of corner frequencies that this filter is capable of. It could be up to a 209 kilohertz 3 dB frequency, or it could be down to 126 kilohertz 3 dB frequency, depending on where in the batch the components came out. Okay. And then there's another type of simulation that you can run, which is a statistical simulation called a Monte Carlo simulation. So I'll show you how to perform a Monte Carlo simulation as well. So instead of a corner simulation, I'm just going to kill these. So a corner simulation shows you what are the edge cases that could be possible. A Monte Carlo simulation gives you a better idea of what's the statistical distribution that would be possible for your circuit as you manufacture, say, 1,000 or 10,000 of these circuits. What would be the statistical distribution of whatever parameter that you care about? Now, of course, you would have to know what the statistical distribution of the underlying components is, which it's not the easiest thing to find, but it's not impossible either. So supposing that you know what the distribution is, then you can run a Monte Carlo simulation. So let me just show you how to do that. So I'm going to right click on this resistor, and instead of showing the corner value, instead of punching in the corner value, I'm going to punch in a random value. So there's a Gauss function, which generates a random variable of a certain distribution. And I'm going to call the argument to this function rsig. So rsig is going to be a parameter that specifies what is the 1 sigma variation of this resistor in percent, or as a fraction, I should say. Same thing for the capacitor. Instead of its corner value, as just a simple percentage. I'm going to call this Gauss function. Gauss, I'm going to call it C sig for the 1 sigma capacitor variation. Okay, so all the other stuff is the same. So I'm going to say spice command dot param r sig equals, let's suppose that the resistor's 1 sigma variation was 1%. And let's suppose that the capacitor's 1 sigma variation is 2%. I'm just making up numbers, but you know, you can figure it out in a real circumstance. And then in order to run a statistically significant number of simulations, we would need to step some parameter. It doesn't really matter what parameter, so I'm just going to make a dummy parameter. S dot step param, I'll call it X. And I'll just run 100 simulations by stepping X from 1 to 100 in steps of 1. I'll add that to the schematic, hit the running man, and watch it run 100 simulations. Each time that it runs a simulation, it randomly generates a new value for each of these Gaussian functions. So there we go. These are the results from those 100 simulations. If I view the error log, then we can see that the corner frequency is varying some amount. Okay. Now, unfortunately, LT-Spice does not have any tools for viewing, say, a histogram of this data, but that's okay. This is easy text. You can just take this text and punch it into, say, Excel and plot a histogram from Excel, or you could find one of any number of histogram plotters on the internet. Okay, so that's not too hard to come by if you want to do statistical analysis. Okay, so any questions there? So that's showing how you can kind of verify that a circuit should function in the face of parameter variations with manufacturing or the life of the circuit or what have you. And that's another thing that simulation is really, really, really handy for, because it means that instead of having to build, say, 100,000 circuits before you find that some of them fail your specifications, if you can simulate your circuit across process corners or across, statistical variation, then you can at the very least get a good sense of what the statistical distribution of your circuit will be in manufacturing. Before you actually go ahead and build 100,000 of them, you can just simulate 100,000 of them and verify that, to a reasonable degree of confidence, that the circuit should work under those circumstances as well. Okay, so it's just a rehashing on the old theme that simulation is cheaper and easier to do than actually building the circuit. All right, so let's just talk about some of the pitfalls of simulation. Pitfalls besides simulating the wrong thing. So firstly, it's, I mean, this should go without saying, but the simulator is not going to be happy if you draw impossible circuits. So say, for example, these two voltage sources that are connected in parallel. Basically, that's representative of a math equation that doesn't work. The math equation would say 1 equals 2 if you perform Kirchhoff's voltage law around that loop. And your math would just barf. The simulator would say this matrix is overdefined. In the case of the circuit on the right, you would, if you perform Kirchhoff's current law at the top node, you would get 3 equals 4, and that's also inappropriate. That's not a correct use of math. The simulator actually would not complain about that. The simulator would just give you an extremely large value of voltage, say, 10 to the power of 308 or something like that volts, which is just an artifact of the way that the simulator solves circuits. The simulator uses modified nodal analysis, which means that it's using equations of Kirchhoff's current law, and as such, Well, as such, it views the circuit on the left as being overdefined, and the circuit on the right just creates these ridiculous numerical values. And so sometimes, you have to know what you're looking at a little bit in order to figure out what's going wrong. Um, because the matrix solver uses Gaussian elimination, rows of the matrix are multiplied by some value and then subtracted from another row. When two values essentially cancel, the result is subject to round-off error. Internally, the simulator uses float 64, the IEEE standard, which has a 52-bit mantissa, which gives you about 15 significant digits in decimal. So, say for example, you have two rows, and of course, when you perform Gaussian elimination, you fully cancel one element of one of those rows. That's the whole point. But another row in that, or another element within that row can potentially almost cancel. And when they almost cancel, but don't entirely, then you can end up with very large percentage errors because you're taking two values that are perhaps very large and have lots of significant digits. And after you subtract them, most of those significant digits disappear, and you're just left with one or two significant digits. And the percentage error in those can be very large. And that can result in convergence failure or in just ridiculous values. Convergence failure basically means that as you're running your simulation, it stops and just sits there doing nothing for perhaps several minutes. And then maybe it throws an error or it just remains stuck. And it's really, really annoying. Convergence failures are very annoying because it means that you don't get your answer. Instead, your simulator just hangs. And often you don't exactly know why. Now, the solver does try to do some clever things. It uses matrix pivoting to preserve accuracy and also to preserve sparsity, which is another really useful property for these matrices to have in the interest of actually storing the circuit representation in memory. But it doesn't always work. Like the solver tries to use matrix pivoting to preserve accuracy, but it doesn't always do it right. And so because of that, you want to avoid circuits that make some values, in other words, currents or voltages, become excessive, right? You don't want to have a circuit where you have currents of, say, 1,000,000 amps. Firstly, why would you do that? Like, there's no real circuit that would be appropriate for. But secondly, it can cause numerical errors that can then cause your circuit not to simulate correctly. Now, another thing that you can do, if you have problems with your circuit simulation not converging, you can also try using the alternate solver. The alternate solver can be specified by going to the control panel, that's the hammer button, and clicking on the Spice tab, and then selecting the alternate solver instead of the normal solver. The alternate solver uses the Intel extended precision, which is an 80-bit float, which has a 63-bit mantissa instead of a 52-bit mantissa. So that gives you an extra 3 significant figures, which quite frequently, it turns out, is enough to make it so that a circuit that wasn't working, that wasn't simulating, now does simulate and converge. The downside to the alternate solver is that it's a little bit slower than the normal solver, but it is almost always better in terms of making sure that the circuit will actually simulate. Now, there can be problems with your models as well. So remember that the circuit solver is iterative, using the Newton method or secant method or a handful of other methods that have been found to be useful for solving electronic circuits. And because it's iterative, it employs numerical solving techniques. These techniques rely on derivatives, on the derivatives of voltages and currents. So the value of any conductance or of any transfer function of any component, in particular where the component exists within some sort of a feedback network, which is almost every circuit. Almost every circuit has a feedback network. Say, for example, 2 resistors connected in a voltage divider. That has feedback, right? So any circuit that has feedback should have the derivatives of any of their values, any of the voltage or current values, any of their transfer functions be continuous. So the transfer function itself should be continuous, and its derivative should be also continuous. If you use device model equations that don't satisfy that, for example, you can build your own behavioral models if you choose to. You can build your own behavioral models using behavioral voltage sources and behavioral current sources, and you can just type in an arbitrary equation if you want to specify the relationship between voltage and current. But if you specify a relationship that is discontinuous, then it can make it so that the circuit solver just fails to converge and gives ridiculous values or whatever. So I will mention, like, a bad model, it often still does work properly in many circumstances, but then you'll just find some weird circumstance where, you change the temperature of your simulation, or you change, the input voltage to your circuit or whatever, and you just, under some mild change in your circuit operation, the discontinuity that was in that model is encountered, and convergence can fail, and the simulation will just stop, and it'll make you very frustrated, anxious, and angry that the simulation is not working. So you do have to be careful when you select circuit models, or when you select them or when you build them. You do have to be careful to make sure that the model is a good model. This is true of any circuit simulator. Like, the simulator is only as good as the models that you give it. I mean, some simulators are better than other simulators, of course, namely, there is a handful of models that most simulators will ever be exposed to, things like BJT models and MOSFET models and things like that. And simulators have to be sort of massaged by their creators to be good at solving circuits that have those components. But beyond that, if you give a simulator a bad model that has discontinuities and is, has very strongly nonlinear functions, then you can just end up with simulations that don't work. Okay, now on top of all of that, so LT-Spice has a bunch of numerical solver tricks built in. And even if you're even with LT-Spice's solver tricks and with continuous device models, it doesn't always converge on an initial condition during its .op simulations. It turns out .op, like, that was the easiest simulation, right? At least the easiest simulation for us to run. It's frequently the hardest simulation to actually perform for the simulator. It's just that because .op is a prerequisite to all of the other simulations, we take it for granted. But it's actually one of the hardest simulations to run. Now, sometimes if .op does not successfully run, you can help it out. You can specify initial conditions for node voltages and device currents. As an example, you can add a spice command, .ic, set the voltage of node 001 to 0 volts if you wish. And what it'll do is it will tell the simulator, when you perform your .op simulation, set the voltage of this node to 0, not something else. Don't allow it to be anything else. And in so doing, it can help. It frequently can help the solver find that initial operating condition for all of the other nodes and all of the other currents. Additionally, during transient simulations, you can also use the startup keyword to specify all independent sources should begin at 0 to help the .op simulation converge on a solution. So let me just show how that looks. If I do I have a transient simulation somewhere? Here's a transient simulation. So if I right click on the transient simulation command, I can select, where is it? Start external DC supply voltages at 0 volts. And you can see that it adds this startup command to the transient simulation command. And what that does is it makes it so that any independent voltage sources, like this voltage source or any like supply voltage sources or whatever, that they all start at 0 volts instead of whatever voltage that you set them to. That's especially useful for, say, a circuit like this, where the power supply to this op amp is starting at plus and minus 15 volts, but perhaps for convergence reasons, it would be better to start them at 0. So you might change that to startup. There you go. Oops. Startup, okay. And then when you run the simulation, if you look at the supply voltages actually have some ramp time, so that for the very initial starting point, all of the node voltages in the circuit start at 0. And it can help with getting that .op simulation to actually run. So again, you don't always have to do it. Like this simulation ran just fine without doing it. But sometimes your circuit won't converge. Sometimes your simulation won't converge, and sometimes you have to do that. And also, quite frequently you'll construct a model. If you construct a model, quite frequently you'll construct one where a node has an extremely high impedance. Say, for example, you're creating a model that models the behavior of some specialized transistor. Perhaps you've gone into a lab and you're working at MIT or Stanford or something, and you're creating some exotic new compound transistor built on silicon carbide or gallium nitride or molybdenum disulfide or whatever. You create this new transistor and you want to model it. You want to create a model of this transistor so that you can simulate it. And you may have a node that has extremely high impedance. Now, by default, PN junctions for diodes, BJTs, and MOSFETs have a small conductance to ground. In the simulator, it's called Gmin, and its default value is 10 to the power of negative 12. So in other words, it's basically a resistor of value 10 to the power of 12 from every PN junction node, from every node attached to a PN junction to ground. And you would think, well, I'm adding a bunch of resistors into my circuit to ground that aren't actually there. Won't my simulation be less accurate because of that? Yes, but the level of inaccuracy caused by that is, by and large, for the vast majority of circuits, negligible. So it's okay to add that little bit of that large valued resistance from these PN junctions to ground, so that what it does is it allows the simulator to actually solve the initial condition, or at least it helps. Basically, it creates a matrix that is more diagonal, or at least closer to an SPD matrix. Okay, so that is present for PN junctions. But if you create your own device model, you might not have put in PN junctions, so the simulator might not have done that for you. So if you do create your own if you do create your own device model, you may have to add that conductance manually, or create a PN junction inside your model specifically so that SPICE will add Gmin to ground. And also another thing you can run into, sometimes you can create models where the time constant associated with nodes settling is too fast. For example, you can create nodes where the settling time of that node is less than a picosecond. And if that happens, then the time step of a transient simulation can become too small and the simulation may slow down, or it might stop. So interestingly enough, you can often improve the speed of your simulator, of the rate at which you can simulate a circuit, by slowing down your nodes, by ensuring every node has a small amount of capacitance. This does not detract from simulation accuracy, because in real life, circuits have some amount of capacitance anyway. Nothing in real life happens instantaneously. So, if you were to make all of the nodes in your circuit settle within, say, a nanosecond, that's probably not going to make your circuit any less accurate, unless you're trying to model the internals of, a gigahertz processor. But it can make your simulation run faster and converge better. An example of a circuit that would have these ridiculously fast nodes might be a MOSFET, a chain of MOSFET inverters with no gate capacitance modeled. And what'll happen is that the simulator will just go crazy, and it'll select time steps that are way too small, and it will have a lot of trouble, and it might eventually just barf and throw it in your face and say, this circuit won't simulate. The time step is too small. And if not, it'll just run, the simulation will just run ridiculously slowly. So sometimes you have to slow things down. In other words, make things more like the physical reality. And a lot of times making the circuit closer to the physical reality in such a manner makes the simulation run faster. Okay, just how accurate is a simulator? This is a topic that comes up every once in a while. You know, people might say, oh, a simulator, it's inaccurate. It's just a numerical solution. You know, just how accurate is a simulator? And the answer is, well, it's kind of hard to tell. Usually the answer is it's accurate enough. Don't worry about it. But what's it determined by? Well, so again, it runs on a numerical solver, an iterative solver, right? And these iterations for the iterative solver, they converge. With each iteration, it gets closer and closer to the actual answer, but it never actually reaches the true solution. It just converges toward it. In the limit, as iterations approach infinity, it converges to the true answer. So at what point, but I mean, you're not going to spend, you know, infinite time performing infinite iterations. So at what point does an iteration become accepted as the answer? And the answer to that is, well, an iteration is accepted as a solution if it satisfies certain criteria simultaneously for all node voltages and branch currents. So abstol, voltol, chargetol, reltol, trtol, and a couple other tolerance specifications. So abstol specifies the absolute value of current. Voltol specifies the absolute voltage value. Chargetol specifies, you know, a certain number of coulombs. Reltol specifies the relative accuracy as a percentage of a quantity. Trtol is estimated relative truncation error, and this applies to transient simulations. And if you want to know where these tolerances exist, you would see them under the toolbar where it says SPICE. And we have all of these tolerances. We have Gmin setting, abstol, reltol, chargetol, transient tolerance, voltage tolerance, and a couple extras. And you can find any SPICE textbook to find out what these mean. But for the most part, basically, these are very small numbers. For example, abstol is the current. If a current is less than 1 picoamp, then it's accepted as a final solution. Reltol is a relative tolerance. So if a value changes by less than 0.1%, then it's accepted as a solution. If a voltage is less than 1 microvolt, then it's accepted as a solution. I'll note that it has to be less than 1 microvolt or less than, or its change must be less than 0.1% of its value in order to be accepted as a final solution. So for the most part, those tolerances are tight enough. Like they're much tighter than the component tolerances that you'll be dealing with. However, if they're not tight enough, you can always change it. Now, sometimes you might be tempted to loosen these tolerances to make conversions occur faster so that your simulation will run faster. And it does converge faster because you don't converge to as close. You don't spend as much time iterating. However, it often makes it so that the solution that is accepted is too inaccurate, so that for perhaps the next time step in a transient simulation, the next time step is incapable of converging, and that causes the simulation to stop, which actually makes it so that the simulation is slower. So for the most part, loosening the tolerances to make a simulation run faster, I shouldn't say for the most part, but frequently it's not just a slam dunk answer. Like you can loosen the tolerances somewhat, it'll make it run somewhat faster, but if you loosen them too much, then the simulation will just stop. So you kind of have to play around with it if you really want to optimize the speed of a simulation. So for the most part, just don't mess with it for the most part, unless you know what you're doing. For the most part, if you do have convergence failure, which causes your simulation to stop, you can solve it by correcting errors in the component models. So for the most part, what causes a simulation not to converge and not to run is using bad models, models that have discontinuities, models that have nodes that don't have any capacitance and change too rapidly, right? So by correcting those models, for the most part, you can get the simulation to run. And if that fails, then you can also switch to the alternate solver. Another interesting note, frequently more accurate models, for example, BSIM 3.3, converge more reliably than simpler models, for example, the Shikshman-Hodges model of MOSFETs. So that basically comes back to the idea that more accurate models that more accurately reflect reality are often better at converging. Also, more advanced models were developed with better recognition of how simulators actually work, and were the device equations were optimized at least a little bit to make it so that convergence would run quickly. Okay. Oof. All right, some notes. So the LT-SPICE solver, LT-SPICE is the most popular simulator in the world, right? Which means that its solver has been put through the paces. It has been tested on many, many different circuits around the world, and it's been refined to actually work with them. So, I've mentioned before that it takes a little bit of tweaking to get the solver to work with the various classes of problems that the solver is expected to be able to solve. And you don't really know what circumstances it will break in unless it's exposed to all of these different circumstances. And as such, LT-SPICE being so popular has been exposed to very large classes of circuits. And so, it's probably, if not the best, at least one of the best simulators for being able to get convergence because it's actually been put through the paces. If your circuit model, however, is too dramatically different from the types of circuits that people make in real life, in other words, if your circuit is just basically a fake circuit, then you can encounter trouble. But if your simulation is representative of the behavior of a real circuit, it's using real components with real transistors and whatnot, for the most part, you don't have too much to worry about. Just use it. And if you do have trouble, you can refer to these slides to troubleshoot and figure out what's going wrong. Okay, now for some resources, these are some places to learn more about LT-SPICE, figure out not just LT-SPICE, but circuits as well, simulation in general, and just circuits that exist in the real world and how to model them and how to understand them. So there's a bunch of example schematics that come with LT-SPICE. If you look in your documents folder, supposing that you're using Windows, if you look in your documents folder and go into the LT-SPICE folder, there's going to be an examples directory. And within that, an educational directory. You open that and you find a whole bunch of simulation files for just a large collection of different circuits. And there's no like grading objective or anything like that. Just go ahead and open them. Just, browse through them, open them up and run the simulation and click around and, see if you can figure out what's going on in those simulations. If you don't know, you can look something up. That's a really good place to start, just playing around with a bunch of different circuits. Another really good place to find example schematics is the LT-SPICE group. So there's an LT-SPICE group on the internet. It's at groups.io/g/LT-SPICE. And it is a very active group of people who just discuss LT-SPICE, discuss, how to make it work, what is out there for it. And they have a bunch of files. They have a bunch of files of simulations that their members have put together. And the members of this group, a lot of them are really, really highly educated experts in the field of circuit design. And some of the schematics that they share with each other are just really insightful. So I highly recommend checking that group out and downloading the simulations that they've put together, because some of them will teach you a lot. Places to find information for using LT-SPICE. The help file is really good. Let me demo something. So let me just go to LT-SPICE. I'm going to show you the help file. So let's suppose that I drop in a transistor, right? I've got this transistor and I'm like, you know what? I want to make a model for a transistor. So let me just control right click. Oops. Control right click. And instead of a 2N3904, it's going to be my NPN. Okay. So now I'm going to add a SPICE command, .model my NPN is going to be an NPN with, let's say, IS equals 1 femtoamp, forward beta equals 100, okay? All right, now let's say I wanted to model more parameters for this NPN, let's say the early voltage or the collector resistance or a bunch of other things. But I never remember that. I always forget, right? So how do I find out what those parameters are? If I hit F1, then I bring up the help file. And instead of contents, I usually use search. So in search, I'm just going to type in NPN. And it brings up this bipolar transistor. Let me double click that. So bipolar transistor, here we go. Here's an example. Dot model, my NPN model, NPN forward beta 75. Okay. And then there's a bunch of, there's Gummel-Poon, blah, blah, blah. If I scroll down, here's all of these parameters associated with this model. IS, saturation current, default 0.1 femtoamp. Base collector saturation current, default is the same value as the regular saturation current, right? Forward beta, emission coefficient, early voltage, the corner for the forward beta high current roll off due to high level injection, high current roll off coefficient, and so on and so forth. All of these different parameters that you can go through to model every single little detail of the behavior of this transistor if you want to, okay? So this is like the help file is just a great place to find all sorts of different stuff about how to use LT-Spice. Okay, so I highly recommend if you forget something, just hit F1 first before anything else. Okay. Now, there's also a great website called Undocumented LT-Spice because there actually is a bunch of stuff in LT-Spice that's not in the help file. Basically, the person who made LT-Spice was not the most concerned with documenting things, but rather more concerned with building a good product first. As a result of that, there's a bunch of stuff in LT-Spice that's not very well documented. And if you want to find out more about it, you go to this website, ltwiki.org/ title equals undocumented _ LT-Spice. It's a great website to check out a bunch of neat features in LT-Spice that you won't find in the help file. And because LT-Spice is such a popular program, you can find many books. There's probably at least a dozen books on how to use LT-Spice, and just as many YouTube tutorials that you can find on how to use it. Okay. And if you want to get help, let's say you have a question and you want answers, you can go to the LT-Spice group, the one that I mentioned earlier. And if you want to know how circuit simulation actually works, I would recommend a book called Circuit Simulation by Farid Najm. It's a really good book for understanding how circuit simulators work. It really gives you a deep appreciation for how this stuff actually happens. Okay. All right. So let's just show a brief example of like getting started with something quickly. So here's a pretty sophisticated component, LT8316. It's a product that I designed. So I'll show you how to start a simulation with it. So I'm just going to add a new schematic. I'll go to the add component dialog and I'll type in LT8316. Okay. Now, if I just press OK, I added to the schematic, hit escape. I added to the schematic and I have no idea, like I have a ton of pins. I have no idea what to do with the chip. It's going to take me a long time to figure out how to wire it up. I'm going to have to open up the datasheet and read the entire datasheet to figure out what to connect each pin to, what the component values should be, and so forth. And that just takes forever. Okay. So instead of doing that, I'm going to go back to the add component dialog. And instead of just clicking OK and adding it to the schematic, I'm going to go to this button here that says open this macro models test fixture. If I click that, it opens this schematic of basically a default circuit that uses this component. And it has it hooked up already. Here's a transformer, here's a power transistor, here's a snubber, a third winding on the transformer with a diode that powers up the chip, a voltage divider, and all of this stuff. Here's a load resistor. And I can just hit the running man and just get started immediately, trying to figure out how to use this component. Okay, and immediately I get to see, you know, the behavior of the chip, get to see the output voltage, you know, all of that stuff. Okay, so that's a really good way to just get started, get up and running really quickly without having to learn everything about a component, is just to use the component's test fixture. Okay. All right, so some final notes. You probably won't remember half the things that we discussed, but that's okay. Even out of the box, even with just minimal skill, LT-Spice is still a power tool. And really just focus on learning what you need as you go, and you'll just keep getting better at it. And it's much more powerful if you know how to use the hotkeys. If you just keep on using those buttons with your mouse, it's just so slow. It's just so slow to use the mouse to select all the tools, and you'll never be a power user. If you want to be a power user, you want to be efficient and not spend forever on things, learn the hotkeys. And LT-Spice, you know, it's the most popular simulator on the planet, so you can find help and examples in many places. All right, so for some quick bonus, I want to show you how you can use LT-Spice for some things that it wasn't intended for. So we can do SIR modeling. The SIR model is a model that epidemiologists use for modeling the spread of a disease within a population. So pretty appropriate for some of the recent world events. So the SIR model models 3 parameters: how many people within a population are susceptible to a disease, how many people are infected by it, and how many people have recovered and or died. And the model incorporates 3 nonlinear differential equations, namely the time derivative of the infected population is some constant times how many people, the product of how many people are infected and how many people are susceptible, minus some other constant times how many people are currently infected. Okay, so this is one differential equation. The time derivative of the susceptible population is some constant times the product of the infected population and the susceptible population, and the time derivative of the recovered population is equal to some constant times the infected population. So 3 nonlinear differential equations, but guess what? Spice is a nonlinear differential equation solver, so that means we can use it. And the current that feeds a capacitor is the derivative of the voltage across it. So we can represent each of these 3 differential equations as a current source feeding a capacitor. So let's show how to do that. I'm just going to go ahead and let me stop this simulation. It's taking too long. I'll just zoom in to show you what it did. Okay, so let me just close that, I'm going to create a new simulation to represent an SIR model. So here I'm going to create a current source. Actually, no, this is going to be a behavioral current source. So BI for behavioral current source. And I'll add a capacitor and add a ground here and a ground there. Okay, so this node is going to be the susceptible population. So I'll call this S. The value of this capacitor, I'm just going to set it to 1 nanofarad. And I'm going to type IC equals 330 meg for 330 million. So this is going to be representative of the US population. We have 330 million people in the United States. So this node voltage is going to start at 330 megavolts, and that voltage will be representative of people, okay? Now, what is this current going to be equal to? It's going to be equal to minus the voltage of the, how many people are infected times how many people are susceptible, divided by some constant divided by the R naught times N. Okay. All right, so that's that that's that current source. I'm going to copy this and paste it. I'm going to call this the infected population. And this one, its initial condition is going to be, say, one person infected. Now, this one's current value is going to be equal to the infected population times the susceptible population divided by same parameter. Minus 1 divided by that. Okay. And I'll copy and paste this again. And this one will be the recovered population. And this one is just going to be initially 0. Okay, this one's just going to be the infected population divided by that parameter. Okay, so let's just set up some parameters. .param, let's set the R naught of this disease to 2, and this infectious period to 7.21 days. And we're just going to run a transient simulation for, say, 1 year. This is going to be 365 nanoseconds. Okay, now if I did everything right, if I punched in the, oh, what did I not do? Oh, and okay, fine. So that's going to be the population. Okay, there we go. Let's go ahead and, okay. So the susceptible population starts off at 330 million and eventually comes down to about 67 million. The recovered population starts at 0 and eventually comes up to 263 million. So 263 million divided by 330, that's about 80% of the population infected after approximately, let's just call that 200 days. And the peak infected population is around about 50 million. Okay, and you can play around with the parameters. You can play with the R naught. You can play with the infectious period and the total population, and so on and so forth, to get it to kind of be representative of the current population. The spread rate, of course, changes with behavior, so it's not actually a constant. But you get the idea, right? So you can use SPICE. You can use a circuit simulator to simulate population dynamics, or to simulate epidemics. All right, so that's pretty cool. And you can also use a simulator to model a heater, right? So I'm not going to run through this one, but but you can create a simulation to model the temperature of an oven, let's say, where you model the thermal capacity of the oven with a capacitor and the thermal resistance of the oven with a resistor. And just measure the temperature and pump power into this thermal network. And the current of this source is representative of the power being delivered into that thermal network. And the voltage of this node representative of the temperature. Okay, and you can set up, say, a state machine to turn on and off the oven such that you model the behavior of the oven. Okay. All right. For a quick appendix, these are my hotkeys that I use for editing schematics. These are my hotkeys that I use for editing symbols. These are my hotkeys that I use for viewing waveforms. And these are my SPICE defaults. Notice that all of the settings for the tolerances and so forth, all of these are default. The only thing that I have that's different is the use of the alternate solver instead of the normal solver. And normally I save everything. If you go to the Save Defaults tab, I save everything. That's because sometimes if you build up a circuit with hierarchy, if you don't have those selected, then it won't save anything inside a subcircuit. And if you're trying to troubleshoot a circuit, that's really annoying not to have everything saved. So I just leave everything. I just save everything. Okay, that's it for my presentation. Hopefully hopefully that kept you guys entertained enough. Let's see how many people. Does anybody have any questions?
There's so much to take in. Thank you once again for coming.
No worries.
Yeah, it's absolutely mind-blowing compared to what we're introduced to, and just sort of like, it's not even scratching the surface. I mean, it's like glancing the surface when we first get to talk about this. So I definitely really appreciate the deep dive. And
oh, absolutely. Absolutely. Yeah, it's a great tool. One of the things I'll mention though, so Spice is if you're a beginner to Spice, you open up LT Spice and then you're like, well, how do I draw a schematic? Or how do I like draw a layout? And you'd be somewhat disappointed to find that LT Spice really isn't the right tool for drawing a circuit layout, or for dropping a microcontroller down and specifying component packages, say an 0805 resistor or a 1206 resistor or any of that stuff associated with the physical construction of the circuit. And you know what? That's not what it's for. It's a really powerful tool, and there's a lot of stuff that you can do with it, but there's a lot of stuff to do outside of actually drawing your circuit. A lot of stuff to do with verifying your circuit, verifying that your idea works, verifying that electrically it is, it's appropriate, right? And so that's what it's for. It's for being able to draw like current sources and voltage sources, and verify ideas, and verify that electrically a circuit is at least capable of working. And then once you've gotten to that point, then you can step forward with more confidence in drawing the schematic again in, say, KiCad or Altium or Eagle or whatever other program, drawing the schematic in that, specifying the packages, and then drawing the layout. Right. So within this whole ecosystem, LT Spice is just one component, and you can do a lot. You can do an absolute, bang up job in LT Spice.
All right, great. Isaac, Rodrigo, Mar, any questions from you guys before I think we wrap it up for tonight?
I don't have any questions. Just thank you again for showing all the things that LT Spice can offer.
No worries. This is not all.
Well, then a lot.
All right. So if that's it, I'm going to call it a night.
Yeah.
Dude.
Yeah, thank you again a million times, and we're really glad to have this recorded as definitely a great resource for people, and yeah, hopefully we'll get to see you in a classroom sometime soon.
Great, I look forward to it.
All right, then yeah.
All right, have a good night, guys.
Yep. All right. Good night, everybody.